Alrighty. Welcome, everybody. Hey, guys, what's going on? Memes here. Yes, yes. Very, very informal here. So what we're going to do is, rather than just have oh my God, I'm talking. Oh, obviously a professional YouTuber. You're going in your own ear there. That sounded wrong. But I digress. So what we're going to do is, rather than just being a random person, again, with far too many links and saved and unsaved. Let's actually organize this into a computational notebook. Why? Because we can. Uh, that and the Wolfram Notebook Assistant seems to be doing the job that we needed to do. So let's see. Let's start. Hmm. We had we had another document that we were claiming a bunch of things. Well, let's just do it. Let's go back to start, shall we? All right. So let's, hold on, let me adjust my window over here. All right, well, I get big so I can actually see the stuff and things. All right, this should be good. Okay. Let me share with the class. Boom. Share screen, window, boom. All right, so let's do this. Let's give it a snappy name. How do we do it? Title. The spherical God cow. God. So going to hell. And the quest for more curvature. Let's well, that's a quote. I'm attempting to follow the general scientific curricula and layout. Basically, only the first word is titled, and if you have a name or something. All right. Spherical God cow and the quest for more curvature. All right. So let's give it a little jaunt. What should we do? All right. Da 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 da. Section. All right. We explore the interesting coincidence that the mass energy of the Higgs boson, when turned into a literal spherical cow of energy density using the associated Higgs bosons, Higgs Compton wavelength. Let's see. Explore the interesting coincidence: the mass energy of the Higgs boson when turned into a literal spherical cow of energy density. Should be semicolon using the associated Higgs Compton wavelength. Induces curvature on the approximately 1 meter scale. It's approximately, I should do control boom negative 1 reciprocal meter scale. There we go. Yeah, we want to be concise and everything. Uh, hey, see, that's one of the big things. Is just all right. What's the difference? It's like we have all these different tools now. And here's the thing: I can go into chat and stuff, and it's gotten a lot better over the time. I'd be like, construct the Higgs Lagrangian or something like that. What is that? Hey, you're changing potential and kinetic energy. Okay, I can have it say it, do the same things that it'll repeat on Wikipedia. It's like, okay, do I know how to construct that at least using the current tools? And it's like, I had to have it walk through. I'm like, all right, show me where all the dimensions are. Show me our like normalization scheme and everything. And then you realize very quickly why many physicists set h bar equal to c equal to 1. There's a lot of factors to keep track of. And just from my own knowledge, I'm like, all right, it's saying these things. Let me trust but verify. Go through, do the calculation. Go through, do the calculation. Go through, do the calculation. I'm like, all right, so after about an hour, it's like, all right, I got a Lagrangian with no change in the energy, so it outputs 0. And that was one of the most beautiful zeros I saw, because I managed to get everything to finally line up. Was it useful at all? No, I didn't really change a thing, but I at least went through the exercise to see the different pieces and what's going on. And it's, I don't know. Again, I'm not a professional physicist or something. I attended the Wolfram Summer School probably just because, well, I think people kind of thought, but yeah, I was an entertaining person to get along with. And I think my friend Duvid said that I might be the minimal amount of interestingness that can try to communicate with Steven. I don't know. But hey, Poindexter. Welcome, K-Shell. Good to see y'all. This is going to be doing a little bit of vibe coding, if you would. So what are we doing? We're going to take some of the conjectures we've had. And again, I can go through and do all these different calculations, but if I'm going to be doing this within the Wolfram language, and they do have a new chat assistant available, and it seems to be working better than the initial review. I got to be open and honest. They had kind of rolled it out, and they let some of us at the summer school kind of pre-test it. It was okay. It had something left to be desired, in my opinion. And a lot of like the chat, I think it was 4, 5, 4 something at the time. It tended to do a better job. Now, with a little bit more experience, I can basically just kind of ask it to see what's going on. And again, if you have an LLM plan with either like Chat Gemini or whatever these AI agent-based models are, you should, if you have a Wolfram subscription, be able to go in and do a lot of this. And again, whatever your personal preference is, it's just the benefit of having your tech CEO be Stephen Wolfram, who uses on a frequent and regular basis. Apparently, you can still open a version 1.0 notebook, and it should work. It can cross compatibility in multiple versions, so okay. And full disclosure, I am not currently at this time a paid Wolfram spokesperson. Who knows? Maybe I got out of corporate sales, but if I ever were to go back, maybe that wouldn't be a bad thing. All right. So what are we doing here? All right. So we've got that. Let's save it, number 1. So number 1, we'll give it a name. All right. Let's call this. Can I do quotes? I just copy and paste it. I'm very lazy. All right. Save as. And request some more curvature. All right. Boom. There we go. And file, save to cloud. Just because computers can occasionally have things that go wrong, but we're going to go through and we're going to go through some of our interesting conjectures and just, I don't know, I just save. Any time oh God, it's got a string in it. Hold on. So we need to take off our parentheses. Okay. Boom. And the question mark curvature. Save. All right, there we go. It worked. All right, so what are we going to want to do? So number 1, we're going to want a little new section here. Boom. Put that over there. Now we're going to get our little notebook assistant going. Let me see. Will it even show help? Notebook assistant chat. Okay, it's giving me. Hold on. It's doing a little thingy here. Let's see where we are. Okay. Oh no, one of my windows just froze. That's not good. Let's see. Can we open up? I'm sorry. I want to reopen the window. I like my little music in the background. So there we go. All right. Apologies. How can we vibe code if we don't have a little vibe music? I'm sorry. It's all copyright to me. Okay. So let's do this. Oh God, let's do the terrifying thing. Okay, I've got my little other chat here. No, we don't know that. Yes. Okay. Let's I need a little bit more like this. All right. We explore this relationship and the and the potential, because we can do this for basically just about anything, and the potential explore this relationship and the potential to conjecture a maximum oh God, a maximum explore this relationship and the potential to conjecture a limit to our universe. Oh God. Verse via curvature induced by the unit limit of mass, of Planck mass. Okay, so now we're actually saying what we're going to be doing in this notebook. Good. I mean, that you would hope so. Save. All right. So, how should we best do this? Okay. Let's start. Please create please evaluate the following expression. I should actually show this. Apologies. Let's stop this. We're gonna live dangerous, my friends. Share the entire screen. Oh no. Terrifying. Okay. So here's a little notebook thing. Right now, if you don't have one of those plugins, I think it's like an extra $20 a month. It's like, again, it's like more than like a Netflix subscription, but ultimately, whatever tool you're going to pay for, if you use the tool and it's worth it to you, that's the thing. All right. Please evaluate the following expression. Let's see what happens if we do this. Higgs boson mass. Let's just do it how we do in Wolfram Alpha. Higgs mass times speed of light squared, so it doesn't confuse it with something else, divided by 4/3 pi Higgs Compton wavelength. That's cubed for our volumetric evidence, so that's our R cubed. All right, go. Does a little thing. So at least in theory, one of the benefits of the Wolfram language, it's basically set up in natural language using English primarily, which most of these AI agents are trained on. And there's one thing they're good at, it's reading text and coming up with pretty dang good next token responses at this point, which raises a whole bunch of other questions. Oh God, I'm sorry, I can't stand seeing myself, so sorry. I'm gonna block this over here. All right, so let's go there. And then we can have our Wolfram Alpha backup page here, just because occasionally it doesn't always do this. All right. So let's see what we got. Oh God, did I just close my little chat thingy? Oh God. Window, assistant chat. Okay, focus. Did I just close it out? Wow. I'm so bad. All right, let's do this one more time. Oh, history. Expose on mass calculation. There we go. Okay. Oh, God. I was going to say, if I have to go through that all again, this is not a very useful tool if I can't go back to what I actually clicked with. All right. All right. So, as you can see, it did the little thingy here, the evaluator here. We can copy this response to our clipboard. Oh, you have it regenerate a response. All right. So, let's say notebook cells, plain text. Oh. Do notebook cells. I'm actually not sure what's going to happen. Let's see. Paste. All right. Please write this as code that will display in a nice table. There we go. That's all we want. Just simple, basic table. Because I know I can go in here and do table, do with a little bracket and everything. And ultimately, I think this is, if you actually understand how to program and stuff like that, you know how to ask the right questions. So it kind of goes back to, was it the old thing that I learned from Thad about the famous Einstein quote that it was allegedly said that Professor Einstein, suppose you need to answer a question to save the Earth. You have 1 hour to do it. How would you go about solving the problem? His response was, I would take 55 minutes proposing the correct question and 5 minutes answering that. I think that's a very powerful thing. I'm getting that general sentiment from many things, in that a lot of times the proper question makes a huge difference. That's an opinion there. So sometimes a well-posed question can be very enlightening, let's say. All right. Back over there. Turn on a window. All right. So, we can just use the grid function to display. Okay, that's basically what I'm looking for. I don't necessarily need a table. I just want it gridded out in a way that makes sense. I mean, this looks like pretty clean code. The question is, will it work? Let's see. Insert and evaluate. Okay. So we have the entity. All right. So we don't need that. We don't need that. All right. I know we haven't even gotten into what we're naming this here. Okay. Higgs mass. Okay. Speed. Higgs mass. Compton wavelength. Boson. Okay. So the entity is the Higgs boson, and we're looking for an attribute, the Compton wavelength. Okay. So we're gridding out quantity, value. Okay, so now we can just change this. It's like, all right. Well, that's quantity. It's the entity, technically. Physical constant. Oh, sorry. Oops. All right, so this is the physical constant. I'll make this bold. I'm going to put bold. I don't know enough. Oh. All right. Back there. All right, so physical constant. Value, blah, blah, blah. All right. So we need some help. Please fix the speed of light so it will properly display. Add a little extra comment there. All right, let's see how this works. All right, there we go. It's actually got it now. Boom. Expressed in GeV there. The question is it correct? I usually don't talk about it in GeV. What's it got? It's got giga electron. Okay. Is that? Oh, per speed of light. Okay. All right. So we want it to be a. All right. Please. Please express the result in joules per meter cubed, because it's an energy density. Because that's energy divided by that, so that should be mass divided by length and time. Because you got energy, and energy is mass, 2 things of length, 2 things of time, and then when you divide by meters, you get your 2 things of length going away, and then 1 goes into the denominator. That's the only way I can do that. It's because literally it's not even multiplying. It's literally just adding and subtracting. As long as it's not more than 4, I'm usually good. All right. So it says it's got the conversion here. All right, let's start and evaluate. Okay, that looks right. Beautiful. Okay, I'd rather not have that. Maybe the GeV is telling us something, but it's still expressed in C, which kind of confusing there, but again, it depends on what you like. So we should just be able to I don't really care about that result, at least for this. I know, I'm terrible. So we're literally just going to delete this row. Okay, other than that, looks pretty good. Boom. There we go. Joules per meter cubed. All right, results in joules. There we go. Cool. All right. See, the benefit of this is it's designed, and I'm pretty sure the more that people use this, and I think this is one of the reasons why a lot of the stuff you see right now, You'll see different free versions. It's like, oh my God, we're going all through all this compute, but I'm like, a lot of this data is probably being going back in to help retrain these different things. And if you get enough perspective, my thing is, okay, if some of the smart scientists in the world are starting to use different agents to help them accelerate things, because it's like, realistically, it's like, I can write this code. I can just take a value for the Higgs boson and just either do that or just define it as the most recent measurement. Just be like, set this to this, set this to this. And it's like, you look at it, I'm like, all right, what are we doing? We're doing a quantity and we're doing a value. We're assigning things. And we're just assigning this. This is set to that. That's set to that. Because we're just defining it over there. Okay. So we've got this. This is the quote-unquote mass energy of the spherical God cow. Okay, where one. We don't need all this. And again, it's an iterative process, but I'm not going to pretend like I could do better. All right, so we get that, we get that. And again, we need to note I think there's a little floating point in routing and stuff going on. They're just using all the digits they have to. Notice that the Higgs is known to about 125 GeV. This is a good approximation. Could be a bit more if we go up another sigma or so. If we go down a sigma, so again, we're doing the best we can with what we got. All right, so we got the Higgs constant wavelength, blah, 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 blah. We don't want that. All right. So, all right. So we've got that stuff there. We can just do this. We hit our code. Okay. But we have the ability to show our worker. The assistant's work. Just prompt dependent. All right. Save. All right. So at least this took a couple prompts, but again, we need to specify, and I'm pretty sure it also associates each notebook. It can actually associate across notebooks as well. But this is really one of those things, and again, I kind of learned this from that. If you have the ability to ask a question, you can actually go through, and whether or not you agree with it or not, if you can at least have the code compute, it's at least doing a thing. Might not be right, might not be useful, but at least the code runs or the code doesn't. That is the superpower that I've learned. And there is something magical about going through, it's not working, and all of a sudden, it works. I can see why that can be a very addicting thing, especially if you get into it. So, but yeah. And again, I think part of it is how you look at stuff, because at least for me to learn about, okay, let's actually open the code. What are we doing? So the way I view it is we've got stuff. What is the stuff? Within the realm of physics, stuff is the things that we can measure or deduce from measurement, our physical dimensions of reality. Now, I got the pro tip from Thad a few years ago that from all the different constants of nature, from how we construct things, you can boil them down to 5 dimensions of measure. Time, okay, space or a length, electric charge, mass, and temperature. The benefit of that is you'll see like when I see like joules divided by meters, giga electron volts. Well, electron volts, giga electron volts, mega, kilo, whatever, and joules, they are both the dimension of energy. They have different numerical values because of how they've been constructed. And again, much of this construction is a result of our human biases of, well, we exist, most human beings are within about 1 or so meters. Usually aren't that many people that we know of that are much more than like 3 meters tall, and there aren't many folks that are usually that much shorter as a grown adult of a meter. So we exist on, I don't know, tens or hundreds of kilogram scale and stuff. So hence we have our units. So one of the interesting things and kind of the whole point of this was when you're taking something fundamental, and like when you're taking something like the Higgs boson or like the Planck mass, we believe those are fundamental things. Now we've measured the Higgs boson. When I say that, we've observed decays that line up with what we believe to be the Higgs boson, aka our detector went click, and there was a bit more of events that clicked that were recorded, because again, at the Large Hadron Collider, they did the upgrade, but before the upgrade, they literally threw out, I think, they only record 1 out of like 40 million events. It's either 40 million or 40,000. I realize that's a ginormous order of magnitude difference, but because you can't record everything, because there's so many things. You're looking for interesting things based upon physics as we know it to look for it. So what happens? You get a whole bunch of protons smashing into each other at around to observer like us near the speed of light. Detector goes click, detector goes click. You get a few more clicks around 125 GeV, and we're reconstructing that from a lot of times they'll use like Z bosons, W W and Z bosons, and then you'll have like top and bottom quark decays and stuff. I'm assuming a whole lot of smarter folks than myself have accounted for a good number of things, but the big thing is, if, as Professor Sean Carroll has said, if you're going to relate a mass to something, we're doing the kilogram, okay, maybe the reference density of water, and water being at precisely 1 gram per cubic centimeter, maybe that does solve everything. It would make things a lot easier. I don't have the evidence to say that. I could say that. I may end up having to claim that for certain things, but when you have something like the Higgs mass divided by the Planck mass, you get like 17 orders of magnitude off. It's like, I made a conjecture, but that conjecture literally doesn't hold water unless the universe is referenced by water there. But when you do an interesting combination of things, and again, most of this was Sean Carroll within a particular conversation explaining, it's like, well, he's been mentioning it more and more, at least I'm more aware of it, like the Compton wavelength. I'm like, that's basically the length scale on which the particle has its particle-iness. So, and I learned the concept of the spherical cow from him. I'm like, I just never looked into it. Like, well, what happens? I'm like, okay, you get about a 1 meter-ish curvature with this thing. And again, you could use the reduced Compton wavelength, and it's going to go up to like another factor like 2 pi. So it goes up to, what is this, like 4 meters or maybe 42 meters? Oh, okay. But hey, maybe the answer is 42. It's also about the Planck momentum squared, but I digress. Okay. But that long ramble was, we got stuff. We got physical stuff we believe we can measure. We got like the Higgs mass, the speed of light, the Compton wavelength, blah, blah, blah. Okay. And then that stuff is doing things. The particular stuff and the things that it is doing is going to depend on what you're looking at. But if I don't know what's going on, I'm like, all right, we got some stuff, we got some things, and then I need to look into see the particular stuff, see if we can maybe computationally reduce it into something smaller, just because real quick little thing here. We have where is that? Boom. Do this. So it's like I'm on the dumpster fire. That's Twitter earlier. So if you do something like, you'll see things like the fine structure constant. Okay. I misspelled it. Okay, so it's got this definition here: elementary charge over 4 pi c epsilon naught h bar. So elementary charge divided by a sphere, going at the speed of light times the electric constant times the elementary unit of action. Gives us this dimensionless number. Okay. You don't need to know a dang thing about anything down here to just go through the logical process of being, well, we have a dimensionless number. If this is charge squared up here, down here, that must also be charge squared. Now, oh God, I apologize. I'm sorry. I'm gonna get probably copyright struck for a little Goku in the background there. Hold on, let me go back to my Godzilla music. I'm a very simple person. So it's like, wait a second. Elementary charge squared. This must be charge squared. What is that? Well, it's elementary charge divided by the Planck charge. So the limit of charge squared. And we get the same number because that's literally what it is. So anytime we can computationally reduce something or see a shortcut, maybe we can learn something. So it's the ratio between our elementary unit of electromagnetism with the maximum, our elementary unit of charge, the associated charge of a proton or electron, and its squared relationship to the limit of unit charge, the Planck charge. So it's basically a boundary. So I mean, if we can identify the boundaries within our system, then we can at least identify the corners of the map. That's the general goal. But okay, where are we? Back to our regularly scheduled quote unquote vibe session. Okay, so what are we saying here? Okay. All right. Great. Let's take, let's bring this up a little bit. So let's take that result and divide it into the universe vacuum energy density. Please display in a similar fashion. Let's see what it does. All right. So again, many of these things, it's you go through, you do the calculation. Blah, blah, blah. All right. Let's see. It's common. Oh, see, it went through and it updated. It had some stuff and then it literally rewrote its result. Okay. Let's insert this and see what happens. Okay. So, it's not what I wanted it to do. Oh, wait, no, it did it. It did it. It did it. It did it. Okay. I think that's using the kilogram value because that's kind of high. It should be about 5.35. Please redo using the Wolfram database. For the universe vacuum energy density, because it's just an often quoted. I'm like, yeah, but it's usually it's about 5.9 or 6 times 10 to the minus 28 kilograms per cubic meter. But if you do his energy, and it's like about a little under 3.5 gig electron volts per cubic meter. All right. Oh, it's having troubles. First model I was unsuccessful. Let me search for a valid way. I should probably just ask it to do it from Wolfram Alpha. Okay, it's attempting to look for it. All right. Please query Wolfram Alpha for universe vacuum energy density. I'm literally putting that in quotes because I know it works. Because I go here. Got it right there. Oh, so I use Wolfram Alpha. Here, let's see what we got. As approximately, you can use, okay. Okay, let's see how this works. All right. So I go down here, see how it compares. And start and evaluate. Oh. Oh, we got a little error here. It's our error. 5. Okay, it needs there we go. Let's see if that fixes it. Oh, 5 times 10. There we go. Okay. Well, that's not displaying how I wanted it. It's giving the correct ratio. Or at least pretty close. Okay, let's do this. Let's literally we should be able to compute it from just like cosmological constant as like an extra digit, so cosmological constant and then times the Einstein constant. Or no, we want this. We need to divide it by that, right? All right. So, 1/200,000. That doesn't, yeah, I don't like that. Blah, 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 results in joule, blah, blah, blah. Please fix the output value of the vacuum energy density. All right, this. Wait a second. I know how to do this. Hold on. All right, let's see. Where is this? Hold Hold on. Oh God. Okay, no, does not equal. Oh God. I forgot the simplest thing. The Wolfram language. Wow, I am such. Oh, is it shift? No. Da, da, da. Da, da. Mathematica query from alpha. Start a new line. All right. Equals equals. All right. I'm so dumb. That was easier than I thought. Equals. Wait a second. No. Shift enter. Okay, that's what it was. No. Doing something terribly wrong. Wow. I'm so dumb. Oh, I took this class. Hey, Michael. It's good to see you. Boyd Bushman experiment. I don't even know what that is. Boyd Bushman. Let's see. Boyd Bushman experiment. Says magnetic ultraviolet frequency. Okay, so this looks like some form of method to attempt to create some anti-gravity propulsion of the vacuum. Magnetic arrangement exciting a coil at ultraviolet frequencies. Well, that seems to be where there's a catastrophe, so I don't know. Okay, well, I'm happy to look at some experimental results. It's you never know what you might find. All I know is I've heard some talks. Occasionally, it's like we all of a sudden notice a 20 magnitude increase or just like 20x increase at this particular, I don't know, experimental setup, and it's like we don't know why. So there's plenty of things that are still yet to be discovered. So modified grand sticky. Okay, cool. Let's see, where are we? Oh, why am I so dumb? Hold on. Shift enter. Is it shift option? No. Straightforward. Oh, control enter. All right. That makes much more sense. Let's control equals, control shift equals. Why is it? Wow. The beginning of empire. Open, close, result. Wow, this is so embarrassing. Such a hack. Let's do this. Universe vacuum energy density. Okay. There we go. Boom. That's what we wanted. Compute. All right. Lambda. Universe vacuum. Okay. So at least we know what we have there. So, all right, now we can. Please set vacuum energy density to okay, so aka rho lambda. That's what it is. And what do we want? Express its value. In joules per cubic meter. Joules per meter cubed. All right, slowly getting better. Most of it again. User error. All right. Oh, it wasn't able to interpret it. Okay. Okay, attempts to... Let's see if it works. Well, that didn't work. All right. Unit convert didn't work. Please rewrite the whole thing. So now, I don't know, maybe I should have asked it to correct it. I'm just like, that unit convert didn't work. Please rewrite the whole thing. So I'm like, if it's just using the same code and it doesn't have a defined parameter. So, okay. Let's see. Did it learn? Or did I prompt it properly enough? Okay. It didn't work. Through unit convert, I manually just set the vacuum energy based on the previous. Okay, the rest of the code calculates and displays the ratio along the... Okay, whatever. Okay, so that's everything we want except the vacuum energy density. All right, so it's just setting it to that, so... Controls, ratio, result, oh, I probably should just put units. Stands minus 10 joules per meter cubed. Let's see. All right. Please fix the output of the vacuum energy density so it displays in joules by meters cubed. Let's see what that does. Did not convert. Okay, let's see how this works. Still not doing the thing. You know what that means? I'm gonna ask ChatGPT. Just, well, all right. So, let's just take all this code. All right. How about this? Can you express it? Let's just be unequivocal right here. Express it as a number with an exponential power or not. I'm just gonna add it. Can you do it? If you can't, that's fine. That's all right. We'll go to our friend chat. I feel like this may be working with an older LLM model or something here. It's like, certainly I can do that. Will it work? Oh god, I'm wondering what happens if we start putting this to the test, the trolley test. It's like, you can do this, great. If you don't, lives will be lost. How much BS will happen, or will it be like, nope, can't do it, nope. I don't want 1 over 200,000. Can you express it as 5 times 10 raised to the negative 10 joules divided by meters cubed? I do not want 1 over, what's that, 200,000. If it puts it out 1 more 10, I'm sorry, Will from Assistant. I think we're gonna retell. Well, we're almost over here. This is the thing. People will use what works. It's like, I like this because it literally has the ability to do the computation, but it's, we have 1 more. Nope, can't do it. All right, that was fun. We're outsourcing the Chat GPT. Actually, no, we'll bring up the window 1 more time. We're just gonna put the prompts in. Does it help? Notebook assistant chat. All right, history, but it has sources like this. If it can get up to, I mean, the newer versions of chat and everything, these AI models are freaking amazing. All right, we're gonna do this. A friend chat. Evaluate the following. Please write some Wolfram language code to evaluate the following expression. Now, please write this code in a nice code, so it displays in a nice table. Okay, let's see. Here's a self-contained Wolfram. Oh, now the question is it actually going to work? Again. Okay, module, blah, 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 entity particle. Okay. Oh. All right, well, this is the part it did right first. Let's see. Let's see how it compares. All right. Code. Oh, well, that failed. Hmm. All right, so what are we going to do? We don't need suggestions. It's literally... Here we go. There's my code. All right. Here's my errors. Please help. All right. Let's see. The image are my errors. Please help. I had an exclamation point, so that means it's... I think a lot of this is just, if you're trying to count and be consistent through multiple regimes and stuff, even when you look on Wolfram Alpha, they'll have like some calculational thing. Here's the particle data group listing or something like that. So occasionally these notebooks, or at least assistants, going back and forth between the units seems like, okay, maybe it makes me feel a little bit better about being a human being just because I get confused enough about these units. So I cannot be it to mass testing without... Okay, yes. The mass density without using... But that is it. I'm not looking for a mass density. I'm looking for energy. Okay, what do we think this is going to work? Are we going to come back with no errors or a different error? I'm going to say maybe a different error. Let's see what we got. Oh my god, it worked! Wow. I'm impressed. The only thing it didn't display is C. Alright. Alright. Wow. Great job. Please adjust. I was wrong. So the what's it? Speed of light C displays at in meters per second. Meters divided by seconds. All right. Okay, I mean, it's... Wow. I'm impressed. It was I a lot of times, unless you're asking the absolute precise question, I'm going to assume a lot of times you just use a prompt error. The ability to specify and see how close it gets, because before it's the Wolfram Notebook Assist is kind of doing, and I'm starting to think it is kind of based upon maybe GPT 4.0 or something like that, because it seems to be doing something similar when I kind of have problems. Like this 5.2 are actually, oh, I probably should just be using codecs. Let's see. Will they give us that? So let's see here. Is this better or worse? I like going to the optometrist. Better or worse? Better or worse? Okay, it did it. Nice. Okay. Put quantities. Our expression. Okay, now it's just a question of tidying it up and to be fair, it's again, there's uncertainty in there, but okay. Cool. All right, so I'll get rid of this. Those are some big fails there, but it's okay. We're learning. We're learning, just like our agent friends. Okay. Just see, you can see that it's the same error again and again. It's okay, that didn't work. All right, so here's where we got to about. All right. All right. All right. I'm going for an hour. Mostly just doing things I should have been doing behind the scenes, and we'll get some more interesting things and more entertaining stuff in the future. So I'll do this. I'm gonna save as. Do that. All right, file. Save as. I don't know why it puts in all those weird places. It's like, oh, let's throw it in this folder. Let's throw it in this folder. And then it gets lost, and then I can't find. I'm just going to assume that maybe that's just a Mac file system thing because it's notorious for shifting things around. Again, user error. 2. This is the second thingy. Oh God, the lag is real. Okay. Save. There we go. Wow. All right, so save to cloud. Yes, we're exploring some things, and we'll get to it. And to have it set up in a nice way, I'd rather just not have to do a whole bunch of screenshots and lazy stuff. All right, save. And we can publish to cloud. For a third way, publish to cloud. So we've got some tokens or something. All right. I mean, I think we just did that. All right. Boom. Close. All right. So anybody wants this for any particular reason, let's quit out that. All right. So for anybody that wants it, we got that stuff there. And yeah, that's about all we got for right now. So hey, thank you all for watching. Take care of yourselves. It's a wacky and wild world out there, but let's do it better tomorrow. Peace out, everybody.